Hello everyone and welcome back to Lec14 Modeling and Control of Electric Machine and Drives. In the last lecture we were talking about the modeling of synchronous generators, and we stopped talking last time about the equivalent circuit determination of the machine, what we called synchronous machine testing. So we talked about this last time, how to perform the lab tests requires to find the equivalent circuit parameters of such a machine. So we should go for now. We just learned how actually to use the equivalent circuit to model the machine, and we had a tutorial over this. So take time to review them just to refresh your memory before we jump now to talk about another thing in a row. And if you just recall back what we talked about in DC machine lectures, you should be known now that I will start talking about the power flow in the synchronous generator. Okay, and again we are more concerned here with the generator mode of synchronous machine, so it's power flow in synchronous generator. Okay, so like what we did with DC machine, I will just do it like a chart, and I hope you remember how the machine works in terms of construction and theory of operation, because that's so important to understand what's happening here. So the input power here, the P input, and the input power here is mechanical power because we're talking about a generator mode, and it's going to the rotor of the machine like what we understand, because the mechanical power basically goes to the rotor because you just use an external mechanical source to force the rotor to spin, to rotate. Okay, so the mechanical power you input to the generator goes directly to the rotor. Okay, and now we start losing. So because we're talking about a rotor, so we will losing the P friction windage. Okay, what we call the mechanical losses. The mechanical losses. Okay, and yeah, the F is the friction and mechanical parts, especially the bearings that just holds the rotor while rotating, and the W of the friction was what you call it the windage losses. Like we said before, that is the friction with the air while the rotor rotates. So you input mechanical part to the rotor and you start losing some of it with friction with the mechanical parts, especially the bearing, and with the air itself, what we call the windage losses. Okay, and like we said, the friction windage losses is we most of the time just use it like laboratory tests, we just determined in the lab, or it's using some sort of empirical formulas taken from catalogs and from the manufacturers and that stuff. Okay, so that's the friction windage losses. The rest of it is your converted power. Okay, so that is P converted. Sometimes we call it P developed, so it's P converted or P developed, should be the same. Yeah, and now that is the rest of the power going to the rotor. So you input mechanical power to the rotor, lose some of it as friction before you go into the rotor winding itself, which is the P converted or P developed. After this, we again lose some of it in the rotor winding itself. You have P copper losses, P copper and the rotor. Okay, so that's the copper loss in the rotor because you have current moving in the rotor winding, so it can be calculated like I field squares times R field because it's copper losses. Okay, so it's the square of the current moving in the winding on the field times the resistance of the field winding. Okay, and that's all the power now that is just going from the rotor crossing the air gap to the stator. That's why we call it PAG. AG means air gap. Okay, so because we are talking about energy convergence, the mechanical power goes to the rotor and it's converted to the stator into electrical power. So that's how it works. Okay, you lose some of it in friction and windage, the rest of it is the converted power. You lose some of it as copper losses and the rotor winding, the rest of it crosses the air gap toward the stator, what we call the air gap power. Okay, once this power goes to the stator, you lose also copper losses in the stator winding. Okay, because it's also electric current moving into the stator winding. So it can be calculated at 3I armature magnitude square times R armature. Okay, why 3? Because that's 3 phase, they're not yeah, that keep that in mind. That's important. We didn't do this with the field winding because the field winding fits from DC source. It's not 3-phase. It's just one winding. So it's I field squared times R field. But the stator winding, the armature winding are 3 phases, so we multiply by 3. And please use this. It's the magnitude of the current because we're talking about powers here. So all the powers, guys, are magnitudes. We do not have angles with the power, the active powers. The P's and the Q's do not have angles, okay? Yeah, the apparent power can have angle, the S can have angle, but the P and Q are just magnitudes. So when you're calculating the copper losses in the stator, you just have the magnitude of the current moving in the stator, which is basically here a phase current, yeah? That's phase current, because yeah, we are really calculating everything. We're calculating using the per phase equivalent circuit, so they are all phase quantities here. Okay, guys? After you load this power in the stator winding, just you have your output power at the end, and that should be electric power. Yeah, you know this. So that's talking about the generator mode here and all that stuff. Like we said before, is everything we have lost here, all those together are the power losses. So you're basically having an input mechanical power, output electrical power, and you lose some of them over the way. Okay, guys? Okay. There is some other source of power here we didn't see before, and this in the DC machine, I mean. Here we find, because we're talking about an AC machine, we have another power loss before we go to the P output. We call it the P core. Okay, the core losses. Okay, and this appears with AC machines, like we're gonna discuss it now. Okay, so there is another source of losses here in AC machines. We call it the core losses, to keep it in mind. Okay, so how to calculate everything here? So from here we know how to calculate the losses. So we know how to calculate the copper losses in the field winding and the copper losses in the armature. I don't know the friction one they just given for the problems, and you can just estimate it in the lab. And the core losses as well. Most of the time we just estimate it in the lab, or it is given in the problems, or we just use some sort of numerical models to find it. So don't bother with how to calculate it right now. We're just more concerned about how to understand it, what it is, and what does mean that we have losses inside the core, inside the iron core of the machine in case of AC machines. Okay, so how to calculate everything here, you should be knowing some of them. So the converted power, like we said, we call it sometimes developed power, like we said from here, is equal the mechanical power input. Okay, P input mechanical, and that is minus P friction windage, like we said. Okay, and this can be calculated directly multiplying the torque, the entirely inside the machine. We call it torque of the machine, torque M, multiplied by omega M, which is the mechanical speed in radian per second. Okay, so yeah, so that is the internal torque of the generator. I'm saying it's internal torque because you have the external torque applied by the external mechanical source we use to rotate the rotor. But here is the internal torque of the machine, which should be a counter torque to the applied one, if you remember what I'm saying about. And omega M is the mechanical speed of the rotor, but it's in radian per second, not in RPM. Okay. And for a synchronous machine, you just know this omega M equals omega S, the synchronous speed. Okay. And the synchronous speed can be calculated by converting the RPM by 2 pi over 60 times the NS in RPMs, and this is calculated like 120 F over P. Okay, guys, so you can just find it directly like that. 60 goes here to 2, so that is 4 by F divided by P. Okay, guys, so for a synchronous machine, we don't bother with everything because the synchronous machine, the speed is just equal to synchronous speed and can be found directly if you know the frequency of the grid you are connected to, if you are connected to grid, and the number of poles, which should be just given in the machine manufacturer's catalog. That's it. Okay, so that's how you can calculate the converted or developed power here. After this, we can just find. So we need to find the air gap power like this. It's just B converted from here. So yeah, if you want to find the air gap power, it is the B converted minus the copper losses in the rotor. So should be easy. If you want to find the core losses, and that's the new thing to talk about here. So what do we mean by the core losses? So it's a new thing here, the P core. Okay, the core losses. So it is losses, some power you lose in the iron core of this machine if you have an AC excitation. Okay, and this have just two parts to talk about. Okay, so the first one we call it the eddy current losses, and the other part we call it the hysteresis losses. Okay, so those combined together give you the core losses. Okay, what are those? We need just to understand what we mean by each one of those. So the eddy current losses, what do we mean by it? It's just the eddy current actually is the current induced in the iron core as a result of being subjected to time varying magnetic field. So remember, like we said before, that the Faraday's law, that if you have a conductor is crossing a time varying magnetic field, an induced voltage will be just induced into it, and that will pass some current into it if it's closed. Okay, so the iron core itself, yeah, it's a poor conductor for electricity. It's not copper, it's not aluminum, but yeah, it still can conduct electric current somehow. So it is a small minor current. It's not so much current that can move inside the iron itself, but you have some current moving there. Okay, and this current causes the iron core to heat up. You have more thermal losses here. So that's what I mean by eddy current losses, because you'll have some current moving inside the core itself because it's subjected to time varying magnetic field. Okay, and from the lab tests for this kind of losses, they just found out this the eddy current losses, P eddy, is just directly related to the square of the frequency. Okay, and that's why we're talking about this appears only in AC machines most of the time, because you're talking about you should have some frequency, some time variation of this to be subjected to. Okay, so it appears more in AC machines actually. So that's what I'm talking about. So this part, which is the eddy current losses, directly related to the square of the frequency, and that's very significant with the frequency. So while the frequency goes up, this eddy current losses goes up. While it goes down with it. Okay, guys? So that's the eddy current losses. What about the hysteresis losses? So the hysteresis losses is basically the power losses required. Okay, or let me say it's just the power required, because it doesn't mean say power losses required. So it's power required to redirect the dipoles inside the core material to be aligned with the applied magnetic field. What is this? If you have just an iron core like this, so that's an iron core, okay, and that's what we're talking about. We have losses inside it. We call it the core losses. Yeah. So it's just the material of the iron core itself has its ions, different ions with different polarities. Okay. So these ions inside is just forming, because they are different polarities, you should be having each two of them are just connected together, just attracted together. So you should have some sort of a north and a south pole like this, a north and a south pole like this. Okay, they're just attracted to each other. Okay, the internal construction of the material itself. It just have like those. They are just very, very small stuff, yeah? But if you just have a coil wrapped over it like this, okay, and you have current moving into this coil, now you have in a magnetic field applied, external magnetic field applied, so you will have some sort of magnetic flux lines moving around here. So for example, you have a north pole here and a south pole here. What will happen is just those internal dipoles will try to just realign to be just attracted to the other poles. So this north pole, for example, will be try to attract it to this south pole, and this south pole will attract it to go to the main south pole outside and go on, okay? So those guys will be just, if you see them like this, so they will be just trying to align themselves like this, okay? So they will be all aligned with the external field, the S, the N. So you will find all the time all here will be S's, and all those will be norths. Okay, guys? So you just aligned with the magnetic field coming from outside here. And this happens with each cycle because, you know, if you're talking about this current going into this coil is AC current, that means it just will keep changing polarity each half cycle. It's sinusoidal wave. Sometimes it's positive, sometimes it's negative, yeah? So the poles are just changing. That's what I'm saying. So each half cycle of the current you're applying into this, those dipoles will be just going around. So sometimes it's just adjusting itself to this, but when this south be north in the next half cycle, and this north will be a south in the next half cycle, those dipoles will also just rotate to align with the new magnetic field. Okay, guys? So you need some energy actually to cause those dipoles to align with the external magnetic field each time. And this is taken from the power you're just inputting to the system. It's part of your losses. Okay, guys? So those are your core losses, the eddy current and the hysteresis. For you to know, it is just also experimentally proven that the hysteresis losses directly related to the frequency, not the square of the frequency like the eddy currents, okay? So it's all depending on the frequency, but not as much as the eddy current. Okay, guys? Okay. Okay. So yeah, that was the core losses, how to understand what's happening, what I mean by the core losses and that stuff. Okay, guys? So back again to talk about the other powers we're talking about here. So if you need to calculate the output power of this generator, which would be the electrical power, so the P output of this generator, which would be an electrical power. So because we have now talking about AC power, so we have the three different forms of electric power in AC circuits, okay? So you have the power triangle. You have P output, and you have Q output, and this is your S output, and that is the angle theta, which is the power factor angle actually, okay? So you know the idea of how calculating this. So the P output, which is electrical power, as you know, can be calculated like 3 V phase I phase cosine theta, okay? Or it can be square root of 3 V line to line I line to line cosine theta. Okay, so it's just up to you. So because we're using the equivalent circuit all the time, which is pair phase, so we prefer to go with this formula, the phase ones. Okay, so you just use the phase quantities you're just using. So if you use those with the same terminology used with our equivalent circuit, so that should be 3 V terminal IA cosine theta. If you remember, we used the equivalent circuit like this, that is JXS, that is RA, and that is your EA, and here the V terminal, and here moves your armature current. All of those are phase quantities, single phase equivalent circuit, yeah? So this is how you calculate the power. It's in watts, and also time 3 because that's 3 phase. Never forget this, okay? You're calculating Q like the same idea, so Q output should be just 3 V terminal IA sine theta. Okay, it's just coming from 3 V phase I phase sine theta. Okay, which also can be calculated from the line to line, but using square root of 3, not just 3. Yeah. So that is the P output and Q output. Okay. So all the time we're talking about here, the P output is the more something we're talking about. It's the what? The active power. We call it like that. So we call it the active power. Sometimes they call it the useful power, because this power, the active power, is the part of the power that can be converted into mechanical energy. So most of the time you're more concerned about that, but yes, the generator can generate P and Q, both of them, because we know for a synchronous generator that used to feed loads into the system, into the public grid, so we have loads that requires active power and loads requires reactive power, like the motors. Okay, so your synchronous generator should be able to provide both P and Q, and also our generator can be just using to have both of them. Okay, guys. You can calculate S easily. So S as a vector is P output, that's S output, plus J Q output. Okay. Yeah. So you don't have vector for the P or Q. Okay, so they're just magnitudes. But the S can have an angle because just the complex summation of the P and Q. So if you want the magnitude of this, S output is a magnitude, which we need most of the time, will be just like any complex number, square root square of P output square plus Q output square. Okay, guys? So that's the total idea we're talking about here. Okay, so yeah, that is the P output, that is the active power P output. Okay, which is actually, you can also calculate it if you have everything else. So this P output can equal the P mechanical, which is the input power, yeah, minus the P losses. You know this from the power chart. So if you go back here, if you want to find this output power from here, and you know the input power, and you can calculate all the losses, so P out is just basically the P input minus P losses, which is all of them. Okay, guys? Sounds good. So this is how to calculate all of those. Okay? And that's very important to just mingle around how to calculate all the power and power losses inside your machine. Okay, guys? Speaking about the powers, we can now just talk about something very important here, and you should have some talking about it with the power system courses, what we call the P delta relationship. Okay, guys, what I'm talking about this, so let's refer back to our single phase equivalent circuit. Okay, that is JXS, and that is EA, and that is the V terminal, that is IA. Okay, what I did here, I just neglecting the resistance, because like we said last time, it is just XS is just much higher than the armature resistance, so it will be not very poorly accurate if you just neglect it for the sake of some easier formulas to deal with. Okay, so if you neglect RA, like what we said here in this equivalent circuit, you can just write down that EA as a vector will equal the V terminal as a vector plus J IA as a vector XS. That is just the armature voltage equation like we just used before, neglecting RA. Okay, and if you can use this to plot the phasor diagram, so the phasor diagram like we did before, and I'm gonna use the lagging power factor phasor diagram because that is the typical case of using this kind of machine in the grid most of the time. Okay, and why I'm using this? To derive a very important and exciting actually relationship between the power P, electric power, and the power angle delta. Okay, guys, so I'm just having this one, that is the equivalent, so sorry, the Phasor diagram for the lagging power factor case. Okay, and let's just play with this as math of triangles, you know, like this. Okay, so from here, guys, is just, you know, this the angle theta, and just by the laws of the math of triangles, this will also be theta. Okay, and this is the angle delta, which is the power angle, which all the time we'll be dealing with. Okay, that is the terminal voltage, V terminal, and that is EA. Okay, and that is the current IA. Okay, so that is IA, that is JIAXS, and that's it. Okay, so if we just use the laws we're talking about, the laws of just the very simple laws of the math of triangles, you'll be seeing from this that is EA. Okay, so if you just multiply it by the cosine of the angle delta, it will give you whole of this part of the triangle. So this is EA cosine delta. Sorry. Yeah. So that is EA cosine delta. This one, all of it will be EA sine delta. Easy as that. Okay. The same thing we can do with this IAXS with the angle theta. Yeah. So this part also, this one here is IAXS cosine theta, while the small part here is IAXS sine theta. Okay, guys, it's just math of triangles, very, very typical cases used before. But using this, guys, we can just find out very exciting relationships from here. Okay, so this red one's EA sine theta is the same part which equals IAXS cosine theta. So you know that's EA sine delta will equal IAXS cosine theta. Okay, and it's also from here that's this long part EA cosine theta. Okay, and until this one, so this one is your V terminal. Okay, so if you subtract this long part EA cosine delta minus the terminal voltage, I will leave you the small part here IAXS sine theta. Okay, guys, so those ratios can be just found directly from your equivalent Phasor diagram. Okay, simple as this. So from here, from this equation, that is IA multiplied by cosine theta. Yeah. So if you refer back to your power output, which electric power equation, which is 3 V terminal IA cosine theta. Yeah. So this cosine IA cosine theta can be taken from this equation directly. So that will equal 3 V terminal IA cosine theta from the above equation will be EA sine delta divided by XS. Okay, and this give you the relationship P output equal 3 V terminal EA over XS sine delta. That's a very, very famous relationship for the synchronous machine, connecting the P output, the P, with the power angle delta, which is everything else is here like constant, will be just a sinusoidal relationship. Okay, guys, so if you try to plot this so that the P output will be a sinusoidal relationship with delta, okay, that will look like a sine wave. Okay, we're more concerned about the positive part of the sine wave, because the negative part, it just means the power is reversed connection, and this is not happening in a generator. Yeah, that means we're talking about a motor, because the power is reversed, the electric power is reversed direction. That means coming into the machine. That means it's not a generator anymore, it's a motor, and we cannot permit this to happen. So in a typical machine, it's not working like that. and we even have a protection we call reverse power protection over the synchronous generator to make sure this will never happen, because it will damage the machine and even make a catastrophe. Okay, so we're more concerned about just the positive part of the sinusoidal wave, but not even all the positive part of the sinusoidal wave. So there is a very important thing we can just take out from here, is this is the angle delta equal 90 degrees, or pi over 2, yeah, from a sinusoidal wave like that. So before this, like you've seen here, with the increase in delta, so while delta increases going like this, the power also increases, and that makes sense. Okay, like we said before, increase in delta comes from an increase in the load. So if the load goes up, delta, which is the power angle, goes up with it. And from this curve, when delta goes up, the output power of the machine goes up with it, and that makes sense, because if the load goes up, your generator has to generate more output power to meet this increase in the load. But if you keep increasing and increasing the load until delta hits this limit, delta equals 90. From here, with the increase in delta, the power starts going down, decaying. Okay? In this part, we call now the generator is unstable. So that is the unstable region. It's something we call before the out of synchronism, that you cannot hit this limit or the machine will go out of synchronism. Okay, it's not stable anymore. That's very important, especially for power system studies. They use it so much, where you call this stability studies, is how to just make sure that if you have a power system working like that, and if you have a load tripped or you have a short circuit somewhere, now you have a surge, an increase in load suddenly on the generator. Can the generator handle this? Or its power will go beyond this limit and go into the unstable region, and now you have no mean to do but to disconnect the generator from the grid. Okay, so delta equals 90 degrees, we call it the stability limit. Okay, but it's not actually the typical one, because it's just basically we have used all of this assuming that RA, the resistance here, is neglected, so we're neglecting RA. Okay, so the actual limit will be less than 90 degrees, but this is theoretically your limit. So theoretically you cannot go beyond 90 degrees, but practically you cannot even go near 90 degrees. It's less than 90 degrees, because if you just had RA also on the calculations, it will not be just looking like this. Okay, but we got the idea. It is just how to find the relationship between the delta and the P, because that determines how your generator is responding to the load, because delta, we call it the load angle or the power angle. Okay, that is directly related to the load. With the increase in the load, delta increases. So this relationship, this graph, show you how the generator acts to just meet the increase in the load demand. Okay, and how to keep it like that. Okay, so we cannot go beyond this, the stability limit, or the generator will be unstable. Okay, beyond this limit. Okay, guys, so that's why we calling the delta equals 90 here the stability limit. Okay, guys. Okay, so yeah, we call it delta equals 9, so we call it delta maximum. So that is the maximum value that the delta can go on. Anything beyond this and your machine will be unstable. That means it has to be disconnected. Okay, so like we said, it's if RA is neglected, that means we call it like zeros, then the maximum or the stability limit is 90 degrees. But if RA is included in the calculation, it's not equaling 0, delta maximum like this will be less than 90 degrees actually. So you cannot even reach 90 degrees in the practical way of handling the generators. Okay, guys? So that will be meant by the P delta or the P angle relationship. Okay? Okay. And speaking of the load and how it impacts the generator and that stuff, that takes us from here to talk about of how the generator, actually the synchronous generator, connected to loads. Okay, so I call this synchronous generator connection to load. How actually this machine can be connected to external loads. So you have two modes of operation for the synchronous machine as a generator. The first one, we call it the standalone mode, or sometimes we call it the isolated mode. Okay, the other one, we call it the connected to grid mode. Okay, or we call it the parallel operation, because just connected like parallel with a grid. Okay, so that means you have your synchronous generator connected to a load. It's just not connected to a grid and a unified grid like we have in the public system, or it's connected to the system, connected to the grid. Okay, guys, so for the standalone mode, we are talking about one synchronous generator feeding a load away from the grid. Okay, and this can be used for several purposes actually, but mainly you're talking about emergency backup generators. So those are the emergency, mostly the diesel powered backup generators you have for the sensitive loads. So if you have the main electricity coming from the grid cut it off, you use just a diesel powered synchronous generator to feed this load you're talking about. Or it is for remote loads, so you having loads that's far away from the public grid, some sort of an isolated farm or something. It's just very far away to be connected to the main grid, so we just use a standalone synchronous generators to feed the loads in this one. So that's what we call standalone mode or the isolated mode. Okay, for the connected to grid, you're talking about multiple generators connected to the same grid, sharing the load. So you have a big grid, so you have a high number of generators connected to this grid, and all the loads are connected to this grid. So you cannot very much or all the time tell which load is being fed from which generator, because they are all just sharing this. Okay, guys, so that's a typical connection for a synchronous generator, which is we more concerned with most of the time, but also the standalone mode is just something you can find a lot, especially diesel generator used as a backup generator, so you can see those a lot in your work. Okay, so I'm gonna start by talking about the standalone or the isolated mode. Okay, so like we said, we have a generator feeding a load. It's just like that. So if you want to have your equivalent circuit like this, so this is your generator. Okay, that is JXS and that is RA. Okay, and just for reference, this is the internal impedance of the generator. We call it Z generator. Okay, the internal impedance of the machine, internal impedance, which is RA plus JXS. And this is obviously your induced voltage, EA, and here is the armature voltage, IA. I don't need to remember units, everything here is per phase, yeah? And because we're talking about a generator and that's in a standalone, that means you have a load connected to the terminal of the machine. That is an impedance here, Z load. Okay, guys? Here's your terminal voltage. Okay, so like you're seeing here, this is your load, and this is your generator. Just like that. So we're talking about an electric circuit solved to just figure out how the current moves and all that stuff. But that's simple because we have this just a generator connected directly to the load. So all the time remembering, remind yourself just the per phase equivalent circuit. That means that is the impedance of one phase of the load, not the three phases. But they are all three phases, and they are just, we are assuming those three phases of the load is also, so that is for one phase of the load, yeah? So those are just balanced load. That means the impedances of the load are just equal between the three phases, so we can just use one phase to represent them all, okay? For this connection, we're talking about a standalone, so the P that the generator generated, the P output of your generator, okay? I'm calling here P generator, or let me call it again P output. But I'm reminding you, I mean that the generator output power will equal P of the load. So whatever power the load requires, the generator will be just having it. The same idea with the Q. Q output of the generator equals Q load. So for the standalone mode, you just find what are the requirements of the load, and your generator should be meeting them. Okay, so that's what we're saying. The generator produces P and Q to meet load requirements. Okay, so what if the load changes actually? What will happen here? Okay, so let me talk about the load changing for this mode of operation, for the isolated mode or the standalone mode. Okay, so if you go back to this equivalent circuit again, and let's write down the voltage equation. So that is EA equals, from here, IA RA plus J IA XS. That's then turning inside the generator, and it's also plus IA multiplied by the Z load, the impedance of the load. Okay, I hope you just can find that this value IA multiplied by Z load is also the terminal voltage. Yeah, it's the current multiplied by the impedance, and this impedance should be just having also components R plus JX. Yeah, that is your terminal voltage. So what happens with the change in this impedance Z load? Okay, so let me say if load increases. Okay, what happens if the load increases? So if we're talking about a load increase, that means its impedance Z load goes down. That is the definition of the increase in the load. Reduced in the load impedance, because when you're talking about a load increase, that means we are just meaning that the current increases, not the impedance. Okay, so when I'm saying my load increases, that means the impedance of the load goes down, and that will mean that the current will go up. Okay, because you know that IA from this equation we just wrote down here will be equaling EA divided by RA plus JXS plus Z load. Okay, guys, just from here. So if everything is constant and that impedance goes down, this current goes up, like this. What will happen to the generator itself with the increase in current? Okay, so this increase in current resulting in increase on voltage drop over Z generator of the internal impedance, the internal impedance of the generator, RA plus JXS. Yeah, you know that you have an electric circuit here. What happens if this current IA increases? The voltage drop over this impedance RA and JXS will also increase with it, because this voltage drop over this equals IA multiplied by the internal impedance RA plus JXS. So with the increase in this current, this voltage drop goes up with this. Okay, and the terminal voltage of the generator, which is also the voltage of the load, equal the induced EMF minus this voltage drop, IA multiplied by RA plus JXS. So if this voltage drop at all increases because of the increase in the current, this terminal voltage will go down. So as a result, the terminal voltage reduces. And that's something not good at all. Why? Because we're talking about a generator. You need the generator to produce enough voltage or the power at a fixed terminal voltage. Because all your appliances, most of your appliances and loads you're using are just very sensitive to the change in the voltage applied to them. Just imagine you are using a charger to charge your phone, something like that. It's just designed to work at a certain margin of the voltage. If your voltage goes down, that can cause this charger to blow up or just burn. If you're talking about a bigger appliances, and that's much worse if you're talking about a motor or something. If you're talking about a motor, a decrease in the voltage will be just most of the time resulting in an increase in the current of this machine, because the motor has to devote some certain power. So the electric power input of the motor is just V multiplied by I, something like that. So if the V goes down, the current has to increase to meet the power, and that means more current moving into the machine. It can burn it down. So typical wise, we cannot let the voltage, the terminal voltage of the generator is just playing around like that. Okay, but you know what's happening now? If the load increases, the voltage drop over the internal impedance of the generator increases, and that reduces the terminal voltage if you keeping EA constant. Okay, so if EA kept constant, the internal voltage, the induced voltage inside the machine. Okay, so you know what's happening now. If I plot this current, the armature current, which also can be the load current over here, with the terminal voltage. So if the current equals 0 at the beginning of this is your induced voltage. You know what I mean? If you don't have current, the open circuit case, so for this thing, if this current equals 0, there will be no drop over the internal impedance, and that means the induced voltage equals the terminal voltage. Yeah, and that's what I'm saying. So if IA equals 0 at the beginning, terminal voltage equals the induced EMF. But when you keep increasing IA, this voltage drops like this. Let me say, because it will be also changing this rate of decay with the kind of power factor of the load. So that is, for example, for the unity power factor. Okay, if you're using a lagging power factor, that means not R, but you have R and L, that is the defining lagging power factor, like this. So you will have even more reduce in the voltage with the increase in current. But if you have in a leading power factor, which you have means you have R and C capacitor, the decay will be much less. That is for leading power factor. So the decay in this voltage is basically it is also not related just to the amount of current, but also to the kind of a load you are applying. Okay, so if your load is just resistive, that means unity power factor. If your load R and L, that means it's lagging power factor. If your load is R and C, that is leading power factor. So it depends on how much load you have, and that's translated into the amount of current here, and also the nature of the load. If it is R or R and L or R and C, you're seeing like that. But in most of the cases, you're just having decay in the voltage like that, and we just don't like this. We need the voltage to be fixed at the rated terminal value. Okay, guys? So why this happens actually like here, the lagging, so why the nature of the load will be just having impact like that. So for lagging power factor, that means RL load. Okay, it's having more decay, like you see in here, like this. It's just go deeper and deeper because you have increased voltage drop over the internal impedance because you have both R and L. Okay, while the leading power factor load, I'm talking about R and C. Okay, this C, the X of it, if you remember, will be minus JXC, not plus. Okay, and this cancels out the JXS of the generator. Okay, so you have inside the generator JXS, and you have out there in the load, you have R load here minus JXC. Okay, so those guys are partially canceling out, not totally, yeah, but partially canceling out, and that means you have less voltage drop here. Okay, guys, so that's why the leading power factor has much better performance here in terms of the decay of the voltage than the lagging power factor. But unfortunately, most of our loads are lagging power factor loads. Yeah, that's it. So we have to know this. It is totally undesirable for the terminal voltage of the generator to change, most of the time decay with load increase. So yeah, it should be done. If your load decreases, the terminal voltage will increase. So we don't like both of them. So we need our voltage to be just stabilized, fixed, not going anywhere. Okay, guys? How this? We use a control action to do this, okay? But I'll be talking more about this next time. But we now understand what happens if your generator is connected like standalone mode, connected to just load. That's a very simple way of connection, you know, and you can just use the typical circuit equations to describe the performance of the generator, like I said. And we just learned today what happens if the load changes and how this will be impacted inside the generator, okay? And on basically on its terminal voltage, which is a very important thing to deal with when you're talking about such kind of machines, because you're talking about the generator generating power to meet the requirements of loads. Okay, guys? So I'll be continuing just experiencing this next time and see what will happen of the machine in its isolated mode, and it's also in its connected to grid mode, to see how actually we can use this generator in typical applications in both the isolated mode and the connected to grid mode. So yeah, thanks so much guys for joining me today, and I hope to see you next time.